Hi folks, welcome back to Chemistry with Mrs. Mays. Today we're looking at reaction prediction. We're only going to do 3 different types of reactions for part 1. We'll start with a synthesis reaction. Remember, in a synthesis reaction, that means we're putting together elements into compounds. For instance, if we take element A and combine it with element B, then we would get the compound AB. Remember when we do a synthesis reaction that in order for you to write the formula of that compound correctly, you have to crisscross the charges. Let me show you how this works. In our first example, let's suppose that we combine calcium, the metal, with chlorine, the poisonous gas. So we write the symbol for calcium, Ca, plus the symbol for chlorine, and chlorine is a diatomic element, so it has to come in pairs. And what it makes depends on how the charges crisscross. So the first thing I'm going to do is just write my 2 elements next to each other because now they're going to form a chemical bond. But up here I'm going to make a note of how the charges work. I don't want to do this in my reaction because a balanced chemical equation should not have charges in it. My chlorine has, if you look on your periodic table, you can see the charge of chlorine. Oh, okay, we're going to write with a thick line now. Chlorine has a -1 charge. So this charge tells me how many calciums I need in my formula. I just need 1, so I can write in the number 1, but I really don't need to. We can just leave that off. But the 2+ on the calcium means that I have to have 2 chlorines, so let's put 2 chlorines on there. There's the formula now for calcium chloride. Remember, we crisscross the charges to correctly write the formula, and then once that's done, we look to balance the equation. Luckily though, this equation looks like it's already taken care of because I have 1 calcium on the left, 2 chlorines on the left, and on the right, 1 calcium and 2 chlorines. So life is good. Let's do another example that maybe doesn't work out quite so nifty. What happens when we combine sodium metal with nitrogen? Well, I'm not even sure this reaction would actually work, but suppose it did, what would it make? So in our second example, we start off just by writing the symbols next to each other, Na and N. And just like before, I have to look at the charges to make sure that I'm writing this correctly. So for sodium, the charge is going to be a +1 because it's an alkali metal. So sodium has a +1 charge. And nitrogen has to gain 3 electrons to become stable. So it has a -3 charge. So this 3 drops down and across so that I know I need 3 sodiums in this formula. And for nitrogen, a +1 means I just need 1 nitrogen. Again, I don't have to write in that number 1. I can leave that off. So now I have to balance my equation because obviously my sodiums are not balanced, and neither are the nitrogens. So let's start by fixing nitrogen. I need 2 nitrogens on the right side, so we'll write a 2 out front. And that makes now 2 groups of 3 sodiums. So I come back to the other side, and I need a total of 6 sodiums to make this balance. Now everything's good. So a synthesis reaction is putting together elements. So when I make sodium nitride, I have to crisscross the charges so that I can get the correct formula before I balance the equation. Now let's take a look at decomposition reactions. In a decomposition reaction, we're breaking compounds apart into their components. Like our compound AB that we formed in the previous reaction, what if we break it apart? Well, what are the components? The components of AB would be element A and element B. In our first example above, we had calcium chloride. So let's break that apart. Do you remember how we formed the calcium chloride? We started with calcium and chlorine. Now, one thing to take note of in a decomposition reaction and in all reactions is that we need to watch out for diatomic elements. Diatomic elements are the ones that come in pairs, and we remember them with the acronym called Brinkelhoff. So we'll write that on the top of our page. Okay, so put a star up at the top and let's write in the diatomic elements that we have to keep an eye out for. One is called bromine, that's the Br part of Brinkelhoff. The next is iodine, then nitrogen, chlorine, hydrogen, oxygen, and fluorine. When these elements appear by themselves in a reaction, they come in pairs. That means we put a 2 behind all of these when they are by themselves in a chemical reaction. On the other hand, if they combine with something else, then we have to crisscross the charge. This is one of the trickier things in Unit 9 because it's easy to forget to do that. Let's do another example. In this special case of decomposition, I want you to know about the decomposition of metal carbonates. That is, if you have a metal that is connected in a chemical bond to the polyatomic ion carbonate, whose symbol is CO3. So we'll use the specific example here of magnesium carbonate. Magnesium has a +2 charge. Carbonate has a -2 charge. So the formula of magnesium carbonate is just MgCO3. And we're going to follow this pattern. Every time a metal carbonate breaks down, we're going to create the metal oxide and carbon dioxide. Every single time. So for magnesium carbonate, that will look like our metal's magnesium. So magnesium oxide is MgO, and carbon dioxide is always the same, CO2. Now, just to be on the safe side, let's check our charges. Magnesium has a +2 charge, and oxide has a -2 charge. So those two just cancel out. That formula is good. And then carbon dioxide, we don't even need to worry about charges. It's just always the same thing. All right, let's do one more metal carbonate just to make sure that we've got it. So lithium carbonate has to have a different chemical formula because lithium just has a +1 charge. And since lithium has a +1 charge and carbonate is a -2 charge, then I need 2 lithiums to balance out the -2 of my carbonate. So when we break this down, we're going to form first the metal oxide. In this case, our metal is lithium, so I make LiO and carbon dioxide, CO2. But now I have to come back here and check my charges. because we just said lithium's a +1 and oxide is a -2. So to write this formula, I need 2 lithiums to balance out the -2 charge of the oxygen. Remember the crisscross rule? That 2 drops down and across. I only need 1 oxygen because lithium has a +1 charge. Once you're done figuring out your charges, then erase them so they don't show up in your final balanced equation. Or you could do that work off to the side and then write your balanced equation in your answer. Okay, one more type of reaction for now. Let's take a closer look at single replacement reactions. In a single replacement reaction, one element takes away the partner of another to form a new compound. We call this the someone stole your girl reaction, because now she left you for someone else. This doesn't always happen. First of all, it's important to note that metals replace metals. And of course, nonmetals can only replace nonmetals. If you're looking at metals, then we're going to have to first check the activity series to be sure that the metal in question is actually more reactive than the one that already has a partner. If the single metal is not more reactive than the one that's in the compound, then it won't be able to steal that partner away. For nonmetals, we're going to look on the periodic table, and we can see the higher it is on the periodic table, the more active it is. So higher things can replace lower things, but lower things cannot replace higher things. For example, bromine is lower than chlorine, so chlorine could replace bromine, but bromine cannot replace chlorine. Here's an example. In our first example, suppose that we have a solution of magnesium chloride and we put aluminum foil in it. What's going to happen? Well, let's check the activity series of metals and find out. So look on the back of your periodic table. In the bottom right corner, you'll see this activity series of metals. In the activity series of metals, I'm looking to compare magnesium and aluminum. Notice how aluminum is lower on this chart than magnesium. Magnesium already has a partner. And since magnesium is more reactive than the aluminum cannot steal the chlorine away. So in example 1, since aluminum is not as reactive as magnesium, then we have to say no reaction occurs because aluminum is not attractive enough to steal the chlorine away. Literally attractive, as in Coulombic attraction between positive and negative charges. Now let's take a look at aluminum chloride and calcium. That's our next example. Remember to crisscross your charges when you write your formulas. So aluminum chloride has 3 chlorines with my aluminum to balance out a +3 charge. Now we'll check the reactivity series and see, can the calcium steal a partner from aluminum? So we're going to look over here, and calcium is up high, aluminum is down low. That means calcium is stronger than aluminum. So this one's going to work. Example 2, we're going to get now the calcium partnered with a chlorine. And the aluminum's kicked out all on his own now. How sad. All alone. Now let's check our charges and make sure we have the right formulas here. Calcium has a +2 charge and chloride has a -1. So when I crisscross these charges, that's going to put the 2 down here for chlorine, and I just need 1 calcium. So it's CaCl2 for calcium chloride. And we better check our Brinkelhoff elements. Is aluminum a Brinkelhoff element? Nope, there's no Al there. Since aluminum is not diatomic, then the aluminum can just stay as Al. But now we have a problem. We have to balance this equation. So since I have 3 chlorines on the left and 2 chlorines on the right, that makes this balancing a little bit trickier, but don't panic, just cross multiply. Bring the 3 across here and the 2 over here. So now I can fix my aluminum. I need 2 aluminums. So come back over here and put 2 aluminums. There you go. And now I have 3 calciums. So fix that on the left side. I need 3 calciums. Just put a 3 right out in front here. All better. It's balanced now. Okay, one more example. Let's look at an example where we have the replacement of nonmetals. So let's suppose that iron 3 bromide is placed into a container with some chlorine gas. Remember, chlorine is diatomic, so it's not just Cl, it is Cl2. So the question is, can the chlorine take the place of the bromine in this chemical compound? Is chlorine more reactive? Let's check the periodic table and see. So here on the periodic table, we can see here's chlorine and bromine is directly below it. Since chlorine is higher on the periodic table than bromine, that means chlorine is more reactive than bromine. Therefore, chlorine will steal away the partner from our bromine in this example. So here we are back to our example. Now iron is going to be partnered with chlorine, and bromine is going to be left out all alone. Before we start balancing, let's check our charges and make sure that our formulas are correct. On this side of the equation, iron carried a +3 charge. So on the other side of the equation, oops, didn't mean to draw a line, I'm going to still keep a +3 charge for iron. And chlorine has a -1 charge, whereas bromine is now an element, so it has no charge because now it's all by itself. All right, the chlorine charge drops down and across, so I need 1 iron and I need 3 chlorines to go with it. So FeCl3. Bromine is one of those Brinkelhoff elements. It's diatomic, right? It's the very first one in the word Brinkelhoff. So we know that when bromine is by itself, it has to come in pairs. Put a 2 behind it. And now our life is a little bit complicated because I have 2 bromines on the right, but I had 3 bromines on the left. So I'm just going to keep calm, cross multiply, put the 2 on this side, and in front of the bromine, we need a 3 on the other side. So now my bromines are nice and balanced, but the iron also got doubled on the left. I put a 2 in front of the iron on the left, so I have to do the same thing on the right. That gives me a total of 6 chlorines. So go back to the left, and we're going to have to multiply chlorine by 3 so that I can have 6 atoms of chlorine on both sides of the equation. So that's the first part of reaction prediction. In the next podcast, we'll look at the other types of reactions.